Okay, so we will start. So last time we talked about uh, the stability of a numerical method, right? So basically, we talk about uh, absolute stability. Then we talk about drawing the stability region, right? And then I told you that today we will start talking about some other mechanism called predictor corrector method. Right? But before that, we see that when we talk about stability or zero stability of a method, we see that basically the first characteristic polynomial satisfies the Dahlquist root condition. Right? So we can verify that. We did not verify that, we just write the definition. So today, to begin with, let us verify that by using an example, a one-dimensional example, and then we talk about predictor corrector method. So I will begin with this exercise. So let me say y prime is equal to 0 over p naught, let's say equal to t, let's say equal to b, and y at p naught is equal to 0. So let us consider the linear, first order differential equation, which is y prime is equal to 0. Right? So then clearly you know f of x or t comma y is 0. So clearly so the linear multi-step method applied to solve this equation will look like this: aj plus ynj plus bj fn plus j. So fn plus j is 0 for all n and j. So obviously the linear multi-step method will have only this part. It's summation of aj yn plus j. Right. So now what we are going to do is we are going to show that, right, the zero stability or the convergence needs zero stability by using the example. Right? So let me do it as a case 1. Right, so let R be a simple zero of the first characteristic polynomial. You know that is the those roots, right? The roots of the first characteristic polynomial is what we are looking for when we talk about zero stability. So here we will look at a root of a first characteristic polynomial, and so obviously you know it can be simple or it can be multiple. So now we will see whether what if the root of a characteristic polynomial, first characteristic polynomial, is simple. Right? So in this case, you know that we have to show that for convergence, the root absolute value of r should be less or equal to 1. So we shall verify that. So you know that by using this method, you are supposed to find the solution at yn plus p. So then you need to know all the values, right, of on all previous p minus 1 points. So then obviously you take certain values. So because the derivative of the function is 0, so then you know it is constant when you integrate it, and then other stuff like that. So you can take initial value in this form. So that is so then I is basically the norms, right? Okay, so if we take a simple differential equation like this, then our linear multiset method looks like this. So for then basically you have to have initial values or the previous values to compute the present value, right? So suppose you break the interval into n pieces, the last node will be y capital N, right? So then that should be equal to, or that is an approximation for the real solution at B, and that is a constant number, you all know, right? So that's not a big thing, right? So because when you integrate this will be a constant. So the big thing, actually it should be 0, right? Because when you put this initial value, hopefully you will get 0. So basically the solution is 0, right? So obviously this is 0, right? So this has to goes to 0 as n tends to infinity, right? So if we take initial values like this, our solution yn will be of the form h times r to the power n, because capital N is the node, and h is basically the distance between two successive nodes, that is the total distance divided by number of nodes, so n. And because this is 0, absolute value of y, I put h here because just to say that this solution depends on the h as well, right? So if you choose h large, then you choose n small, that's not going to give a better approximation. So choosing h small enough makes n increases, and then you get a more better approximation. So that's obvious so far. So now this is equal to, or this depends on absolute value of r to the power n, and you know that that converges to 0 if and only if r, absolute value of r, is strictly less or equal to 1. Right, so that's the case 1. Now the case 2 is you take r to be a multiple root. Right, so if r is a multiple root, so let us change it here. Case 2. R be a multiple root of the polynomial. So this time we take this as h I R I, right? Because basically in differential equations or difference equations, right? So if you have multiple roots, then you choose the solution as this, right? So this is something may will flow to you, but you can assume that this is how you take the initial values to solve the difference equation, right? So then obviously all these things holds, and then like this is h, there should be an n here, and there should be an n here, and there should be an n here. So this converges to 0. Okay, so here because of multiple root, right, r being multiple root, we choose the initial value as h times I times r to the power I, right? So because again you need initial values at yn plus 1, yn plus 2, yn plus 3, and so up to yn plus p minus 1 to get yn plus p. So you choose all these initial values as h times I times r to the power I, right? So in that case, if you choose that as initial values as that, then all the others are same, right? So you take h as the equally the distance between two equally spaced nodes, and you take there are n nodes here. So obviously the method converges. It means the approximation and the real solution at that point should be close enough, right? When n gets larger, that means the number of nodes get larger. But in this case, because you choose initial values as 8 times I times r to the power I, your yn will be some h times capital N times r to the power n, right? So here you have an n here and then there's an n there, and so n cancelled out. So what you have here is basically b minus t naught to the power rn, right? So this is the difference, right? So in case 1, you have b minus t naught over n into r to the power n, right? In case 2, you have b minus t naught times r to the power n, right? So now this will goes to 0, right? If this goes to 0, also this will goes to 0. But obviously, as n goes to infinity, this one will automatically goes to 0, 1 upon n